Okay, so far we have seen a couple of constructions for union, for intersection, for star and so on, and you have to believe me that these constructions are correct. But for all of these constructions there are proofs that they actually do what we expect them to do. And I will give a proof for the product construction. So I will prove it to be correct. Prove product construction. Remember, the product construction was meant to create an automaton accepting the intersection of two languages. So I have to prove that the language accepted by the automaton AI for the intersection is actually the intersection of the language of the first automaton with the language of the second automaton. I hope you remember the constructions, because now I will use it. And for proving set equality, we have to do two proofs, two parts. First proof is we have to prove that this language here is a subset of the second language. So the first part is subset. To prove that this language here is a subset of this language, we simply take one of the words from this language. So we say let W1, W, call it W, let W from A1 to AN be a word that is accepted by AI. So it should be in the language. It should be in the language, so it has to be accepted. And if it's accepted, there's an accepting run. Then there is a run, an accepting run, accepting run of A1 of AI for W. And this run has the form that we have pairs, so we have Q01, Q02, Q11, Q12, and so on up to Qn1, Qn2. Remember, first component was the state of the first automaton, second component was the state of the second automaton. And the sequence is an accepting run for this W. So that's the assumption. And as the run is accepting, then we know something. The first thing we know is that Q01 and Q02 are initial states of A1 and A2. Then Q01 is an initial state of the first automaton, and Q02 is an initial state of the second automaton. And we know the run is accepting, so Qn1 is an accepting state of the first automaton, and Q2 is an accepting state of the second automaton, because this state here has to be in the Cartesian product of F1, F2, so, and Qn1, Qn2 is in F1 times F2, and that is Qn1 is in F1 and Qn2 is in F2. So this state is an accepting state in the first automaton, and this state is an accepting state in the second automaton. Okay, this we have. Now we have to use the definition of the run, meaning that there should be a transition from each of the subsequent states in the run. Furthermore, what do we know? We know that if we take a state in the run, the state is pair, let's say Qi minus 1, 1, comma, Qi minus 1, 2, so one state in the first automaton and one state in the second automaton as a pair, which is one element here in the run, and the letter AI. Then starting from this state, the following state here in the run should be reachable by the transition relation. So the resulting state is QI1 and QI2. And that follows from the fact that this run here is a run in AI. But from the definition, we know that if we have this, then we know that as this was the result was defined as the Cartesian product of the transition relation for the first and for the second automaton. So we actually know that QI1 is in delta 1 for QI minus 1, 1 with A, and that QI2 is in delta 2 for the state QI minus 1, 2 with letter AI, both with AI. So we know that there was a transition in the first and in the second automaton that actually created this transition here in the product automaton. Now we have compiled all the pieces, and we can conclude that we have now two runs. Therefore, we have a run. We know that there must be a run in the first automaton. Therefore, there is a run for W in A1, and this run is actually Q01 up to Qn1, and run Q02 up to Qn2 in A2. And both runs are accepting. Both runs being accepting. Because we have derived that the first run ends in a accepting state and the second one as well. So using these two facts, we can conclude that both runs are accepting. As both runs are accepting, the first automaton is accepting and the second automaton are accepting, so the word is in the intersection of both languages. So, therefore, W is in the intersection of L of A1 and L of A2, because it is accepted by A1 and it is accepted by A2. So we have proven that this subset relation actually holds. For the second part of the proof, we consider the superset direction, so the other way around. We assume that we have a word W which is accepted by the first automaton and by the second automaton, so it's in the intersection of both languages. And we have to show that this word is actually accepted by the product automaton. As the word is in the intersection, we know it's accepted by the first and by the second automaton, so we know that there are two accepting runs. Therefore, there are two accepting runs. We assume that the word W has the form A1 up to AN. Again, there's n letters, and the two accepting runs of A1 and A2 are Q01, Q11 up to Qn1. That's the accepting run for the first automaton, and the second run is Q02, Q12 up to Qn2. These two runs are accepting, so we know that, for example, Q01 is an initial state of the first automaton, Q02 is an initial state of the second automaton. We know that Qn1 is an accepting state of the first automaton, and Qn2 is an accepting state of the second automaton. And we know that actually the transition relation corresponds to the transitions between the states here. So we can build a new run. We don't know that it's run yet, but we can build a sequence. We can build a sequence and now we combine in this sequence the states pairwise. This one with this one, this one with this one, and so on. So we build a sequence Q01, Q02, Q11, Q12, Q12, and so on, up to Qn1 and Qn2. That's the sequence. And we know that then Q01, Q02, so the initial state here, it's a state in the product automaton, and it's actually an initial state. This one is in Q01 and the Cartesian product of Q01 and Q02, so of the sets of the two initial states of A1 and A2. And this is because Q01 is in Q01 and Q02 is in Q02, the set of initial states of the second automaton. These two statements are true because the runs here are runs of the automata A1 and A2, so we know this condition. Similarly, we know that Qn1 and Qn2, Qn1 and Qn2 are in F1 and the Cartesian product of F1 and F2. Same argument, because we know that Qn1 is an F1 and Qn2 is an F2. Because both runs are accepting, the run here, this one is accepting, so this state needs to be an accepting state, and for the same word, this run here is accepting as well, so this one, Qn2, needs to be accepting, so we know that Qn1 is an F1 and Qn2 is an F2, so we can conclude that the pair Qn1, Qn2 is in the Cartesian product of F1 and F2. So that's for the initial and accepting states. And finally, we know that if we consider the transition relation delta and we check what it does, we assume that for this transition relation we are in the state Qi minus 1. 1, the first automaton, and Qi minus 1, 2 in the second automaton, and we consume Ai, then we know that the state Qi I1 and Qi2, so this pair, is actually in the set that's yielded by this transition function. Question is why? And this is because we know that if we take delta 1 and input the state Qi minus 1, 1, and consider the letter AI, then we know that in this set there needs to be Qi1. Because we consider this run here, and in this run, each subsequent state in this run is actually the result of using a transition. So if we go from Q01 to Q11, using the letter A1, we know that there must be a transition from Q01 with the letter A1 to Q11. And similarly, to go from Q11 to Q21, we know that there must be a transition from Q11 with A2 to Q21. And that's actually what we have written here. So there needs to be a transition in automaton A1, because this is a run of the automaton A1. So we know this, and we know that delta 2, if we are in Qi minus 1, 2, and input AI, so the ith letter of the word, then in the result, which is a set, there must be the state Qi2. Same argument for the second automaton. Each of the states here is a result of taking transition, so we know that there must be a transition from the I-1's state in A2 with letter AI to the state Qi2. So we have concluded that we have this condition on the transitions. We have conclude the requirement on the final states and on the initial states. So we can conclude that actually the sequence that we have defined here, this one, this must be an accepting state of the product automaton. So the sequence constructed must be accepting in the product automaton AI. So the word is in the language of this automaton, AI. And that actually concludes the proof.